we'll be looking at symmetry in the unit circle. Okay, so to start off, let's look at what one of the symmetry properties of the sine function is. So on this unit circle here, I've got the angle line for theta, the orange one, and the green one is the angle line for pi minus theta. I want you to look at the y values of each of these coordinates. So I've got 0.27 on the left and 0.27 on the right. Now, as I start increasing theta, just watch how the y values of each of those coordinates changes. So there, I've increased it, 0.845, 0.845. And indeed, as we go through all the different values of theta, pi minus theta, of course, changes in response to theta changing. And the y value also changes for each of those respective points. What this is really showing is that sine of pi minus theta is equal to sine of theta. That is, the y value generated by the angle pi minus theta, which is 0.655 in this case, is the same as the y value generated by the angle theta itself, again, also 0.655. So this is one of the symmetry properties of sine. Moving on to cos, something similar happens. Again, I've got orange, which was my original theta, and green, which is my 2 pi minus theta in this case. So I want you to look at the x values of the 2 points. As I increase my value of theta, as you can see, the theta changes and 2 pi minus theta changes in response to that as well. Again, no matter what angle I pick for theta, the x value that I get, which is 0.627 in this case, also reflects to 0.627 on the other case as well. So what that is saying is that cos of 2 pi minus theta is equal to cos of theta. Again, one of the cos symmetry formulas. Moving on to tan now, something similar happens. Again, the orange is theta and the green is pi plus theta. So what this means is that as I increase my theta, pi plus theta is an angle on the opposite side of the unit circle, but given the way the tangent function works, the tangent of pi plus theta, which is this point here, will basically go past the origin, past theta, and then onto the tangent line. So as you can see, no matter what value of theta I choose, the value of tan of pi plus theta is the same as the tan of theta, which is, again, one of the symmetry properties of tan. So moving back to our 6b examples, let's look at how some examples can be used to evaluate the sine, cos, and tan of angles that are in different quadrants to quadrant 1. So example 1 is, let us evaluate sine of 5 pi on 6. Okay, so sine 5 pi on 6, the way you go about this is you need to express 5 pi on 6 as either an addition or subtraction of a multiple of pi and an exact value angle. That is pi on 6, pi on 4, or pi on 3. So 5 pi on 6 is simply sine of pi minus pi on 6. Now, visually, when you look at pi minus pi on 6, what that means is you start at 0 and you swing all the way across to pi, which is 180 degrees, and then you swing backwards by pi on 6. Recall, please, that the anti-clockwise rotations are always positive and clockwise rotations are negative. So pi minus pi on 6 means go anti-clockwise by pi radians, and then minus pi on 6 means go clockwise by pi on 6 radians. So what this means is we are in the second quadrant. So this is clearly the second quadrant of the unit circle. Now what this means is that we've actually just got sine of pi on 6. So in the second quadrant, sine is positive, and the value that it takes on is the same as the sine of the exact value angle that it was in the first quadrant. So sine of pi on 6 from our exact value table or special value, special angle triangles is simply half. Moving on to our second example, we've now got sine of 4 pi on 3. So 4 pi on 3 is basically pi plus pi on 3. So how do you get to pi plus pi on 3? Again, you always start at 0, go anti-clockwise by pi, which gets you to the negative x-axis, and then go forward again by pi on 3 radians, which is 60 degrees. What this shows us is that we are now in the third quadrant. So in the third quadrant, sine is negative. So that is why we end up with negative sine of pi on 3. From our exact value table, sine of pi on 3 is root 3 on 2. So the answer is negative root 3 on 2. Moving on to example 3, let's evaluate sine of 7 pi on 4. Okay, so sine of 7 pi on 4, 7 pi on 4 is an angle that is the same as 2 pi minus pi on 4. So how do you get to 2 pi minus pi on 4? Well, you start at 0 and you go anti-clockwise all the way around, so one full revolution of the unit circle. So that takes us all the way to 2 pi, or 360 degrees. And then you go backwards by pi on 4 radians, which is 45 degrees. Clearly, we are now in the fourth quadrant. So in the fourth quadrant, sine is negative. And this is why our next line should be negative sine of pi on 4. So we've got a negative over there, and sine of pi on 4 from our exact value table is root 2 on 2. Therefore, our answer is negative root 2 on 2. Okay, moving on to our second last example, example number 4. To evaluate the cos of negative 11 pi on 6, we first need to use a negative angle formula. So one of the negative angle formulas is that cos of negative theta is simply cos of theta. In other words, cos doesn't care about negatives inside it. So let's first get rid of the negative, which is cos of 11 pi on 6. And now let's express 11 pi on 6 as 2 pi minus pi on 6. Again, using a visual approach, you start at an angle of 0, you swing all the way around one revolution to get to 2 pi, then you go backwards by pi on 6, which is 30 degrees. Now what you can see is that we are in the fourth quadrant. There we go, there's the fourth quadrant. In the fourth quadrant, we all know that cos is positive, and that is why our next line should be cos pi on 6. So now that we know that it's cos of pi on 6, from our exact value table, cos of pi on 6 is root 3 over 2. Okay, moving on to our final example, example number 5. Let's evaluate tan of negative 2 pi on 3. Okay, so as we did in the previous example, let's use a negative angle formula first. So the negative angle formula for tan is that tan of negative theta is equal to negative tan of theta. So in other words, simply take the negative that's inside the angle and move it outside the tan. So we now have negative tan of 2 pi on 3. We now need to express 2 pi on 3 as pi minus pi on 3. Okay, so what does pi minus pi on 3 look like? Well, you start at 0, and then you go all the way to pi, which is on the left on the negative x-axis. Then you go backwards by pi on 3. So what this diagram shows is that when you start at 0, go to pi, and then go backwards by pi on 3, the tan of that angle, you would need to evaluate that by basically extending the angle line through the origin, past the opposite of the unit circle, and then all the way down to the tangent line. And as you can see, that is a negative value over there. And also, what you can see is that this is in the second quadrant. Okay, so now that we know that the tan of pi minus pi on 3, which is in the second quadrant, is in fact a negative number, our next line will now have two negatives. One negative, which is a result of the negative angle formula, and the other negative is a result of tan having an angle that is in the second quadrant. So we have two negatives here. Of course, a double negative becomes a positive, and tan of pi on 3 from our exact value table is the square root of 3. Hopefully, these examples help you understand symmetry. Thanks for tuning in.